Okay, hi, welcome back. I just want to explore some simple harmonic motion a bit more, and particularly the two equations you need to know. Uh, One of them is for the velocity of the particle in simple harmonic motion at any uh, displacement from its equilibrium, and the other one is the total energy in the system. So let's begin with writing down from the last video I did, where we calculated the position of the particle at any point in time t. It was simply a cos omega t, a being the amplitude, omega being the angular velocity, and t being a point in time. Okay, if I differentiate that, differentiate x in terms of t, I end up with velocity, and we had equals a omega sine omega t, and that's negative. Okay, I'm just going to do a bit of a derivation for the velocity of a particle in terms of its position. Okay, so what I'm going to do next, I'm going to square both sides, so I end up with v squared equals minus a will become a squared omega squared sine squared omega t. Then next I will use a trig identity, the Pythagoras trig identity, sine squared plus cos squared equals 1, yeah? So I'll substitute sine squared omega t with 1 minus cosine squared omega t. So let's go ahead and do that. Squared omega squared 1 minus cosine squared omega t. Okay, that's good. Next I'm going to multiply through the brackets. I'm going to distribute the a squared omega squared through the brackets. So I'll do that now. V squared equals a squared omega squared minus a squared omega squared cos squared omega t. That's good. Unfortunately, these omegas aren't coming out too well because the resolution of my writing pad isn't too good, but hopefully you're getting the idea. Here you can see, using a different colour, I've got a squared cos squared omega t. Well, if I took the squares away, that would just equal x. So a squared cos squared omega t is x squared. So I'm going to replace that bit underlined in blue with x squared. So let's just do that. And I now get v squared equals a squared omega squared minus, well, that a squared cos squared omega is x squared omega squared. Great. Next I'm going to take the common factor is omega squared. So let's take that out. Let's factor that out. So I get v squared equals omega squared brackets amplitude squared minus x squared. The displacement of the particle in simple harmonic motion. Okay, final bit is to square root both sides. So the square root of v squared is just v. Square root of omega squared is omega. And then all that goes under a bracket. Amplitude squared minus x squared. Now in your A-level physics, you actually need to remember this. I think it's given in the formula sheet. That's a key formula we need to remember. And that's just giving you a bit of context to where it comes from. Okay, now there is one further thing of note here. A particle is at its maximum velocity when it's in its equilibrium position, i.e. when x is 0. So V max well, if x is 0 there, I'm just going to have the square root of a squared, which is just a. So for the maximum velocity is omega multiplied by the amplitude, okay, for maximum velocity. That's quite good. And then correspondingly, I can take that a step further and talk about the total energy of the system. So the total energy, E, when the particle is in the equilibrium position, it will be travelling at its maximum kinetic energy. It will not have any gravitational potential energy if it's a pendulum. It won't have any elastic potential energy if it's a spring. It'll all be kinetic energy. And in that case, we can say the total energy of the system, ET, is half mv squared, half m v squared. Well, that's when v is going to be maximum, and we can see here that v squared is going to be this term squared. So we get omega squared, alpha squared. And that's another key equation we need to know. The total energy in a system in simple harmonic motion. Okay, one little bit I should really mention is that we can calculate omega squared. So if we need to use this formula, omega squared, this comes from the time period, for calculating the time period of systems in simple harmonic motion. If we rearrange that equation a bit, we can get omega squared for a pendulum is going to be G over L. And then that could be swapped straight into there if that's what the question needs. And also for a spring, for an oscillating spring, it's going to be the spring constant divided by the mass hanging off the end of the spring. And that might go into there. Okay, so you can get omega squared from possibly from the questions. Now I think that's all I want to talk about today. Hopefully you can see. Let me just get that a little bit bigger. So hopefully that gives you a good idea of these two key formulas, which is that one and this one. Okay, you need to know them for your Cambridge International Grade 12 or Year 13 A2 level physics. Okay, hopefully that gives you an idea where they come from, and didn't just pluck them out of thin air. Okay, thanks for watching. Goodbye.